Today we're going over a paper called Metagradient Reinforcement Learning with an Objective Discovered Online. And similar to what we talked about last time, this is a paper on metagradient reinforcement learning. Basically what the metagradient framework allows us to do is to consider not only the updates to an agent, but also how we teach the agent to teach itself. So it's a higher level of abstraction, you could say, from actually, well, the learning of the agent. So to set the stage for what we're going to analyze in this paper, what we want to find is an algorithm that finds its own objective based on environment interactions. So you would have some agent interacting with the environment, and based on what it sees and how it, what the feedback is from the environment, it would update its predictions of this objective. And a benefit of this is that the objective can basically change over time. So if you have an environment that alterates between two states, let's say, your agent could adapt to those changes in a good way. The way we would approach this in the paper, and the way they are approaching it in the paper, is to parameterize the objective function with a deep neural network and then optimize this using metagradient. We're going to go into the details of metagradient in just a few slides, but just at the high level, that's what you're doing. And to set the contrast for preliminary work in the same field, let's say, what we're doing here is we're considering this online as well. So quite popular with these kinds of algorithms is that you're doing it offline, but here, we're not doing it that way, but rather online. And there's a few key differences that we get as a result of this. So first of all, we can apply that to any reinforcement learning environment. So when you're doing it online, you're not as constrained when it comes to what environments you apply this to. It doesn't require a distribution of related environments either. So normally when you do it offline, you would have a distribution of environments, and you need to tailor that specifically to get the features that you require. That's not the case here when we're doing it online, but it's easier to apply immediately. And another really key benefit of this is that you can adapt the objective function as the learning proceeds. So you're not fixed in one objective function, but it can really alterate throughout learning. So to just give some preliminary theory on reinforcement learning in general and how we tend to update that. Normally, when we use temporal difference algorithms, which are quite popular in reinforcement learning, we bootstrap to construct a target G. So the target G is usually the end of lifetime return. So the value function if you're in a prediction setting. And what you would do is you would bootstrap that. The easiest version is basically a TD1 target. And what you do is you say that, okay, our value function or our target is going to be the reward that we get in the next step plus the discounted value of the value function in the next step. So basically we're saying that, it's the reward right now plus discount of what we get in the future. And that's a very common approach to doing this. And you can also roll this out for a number of steps. So you don't necessarily need to do a TD1 target, but you could do a TDN target, for example. And the difference then is that you would have these, you would take the returns that you believe you will get in the future and basically roll out this into the future. At some point, you will still have this value function coming in, but you would discount that more and more as you proceed into the future for this value function. What you do then is you update the parameters of your agent in that case. So basically you parameterize your value function using some parameters theta, and you update those according to the difference between your target and then your parameterized value function as it is right now. And you do this many iterations, and then, based on that, you then converge to a reliable value. So that's, a standard application of reinforcement learning. And what we do differently now is we fully parameterize the update target by a neural network. So G, instead of sampling this from the returns of states, we actually use a function approximator here to get this. And as an input to this neural network, which is how we parameterize it, we use basically a trajectory. So a set of a sequence of steps. And based on that, we try to predict the value of that state. And there's another way you could do this. So this is sort of taking the approach of parameterizing the target, but you could also imagine parameterizing the loss right away. So just to give an example of what the loss and the targets would be in reinforcement learning settings, we have these equations here. So the first one here is if we start with the second one, actually, we can see that this is the TD target. So basically we have the next return and the discounted future value function. So this is kind of what we said that we will be parameterizing with a neural network, but you could also parameterize the loss directly, which would be according to this equation. So the only difference is you take the difference between the target and your current state and then square that. And you can imagine doing that directly and potentially cutting out a step. Both of these are investigated in the paper, but they have a preference for the latter one, which is parameterizing the target. And the reason is that they think it's more stable. This is also something we will see in the results. And the reason why they think this is when you use the TD target as your, when you parameterize your target, your algorithm would naturally converge to that, because what you're doing is you're updating your parameters for the agent to basically approach the target value. If you parameterize the loss instead, there's no guarantee that these values will be small. So you could end up with a very big loss in one case, and that could basically get your algorithm to spiral out of control. And yeah, that would, of course, make convergence properties worse. So that's why they postulate that the target will be a better update or a better fit for this parameterization. To set the stage of how metagradient reinforcement learning works as well, we're going to have a slide on this, and this is something we've been through briefly in other videos, but we're going to dedicate a slide to it here as well. So the premise that it relies on is generally that most update rules are differentiable. So these TD update rules that we're using, you can differentiate them, and if you can differentiate one of them, you can differentiate several. So you can therefore differentiate a sequence of these updates. And if you can differentiate it, you can optimize it as well. So that's the general idea, that you don't just want to optimize the parameters, but you want to optimize the sequence of updates that you do. So basically improve your learning. The way you practically do this is you use something called an inner loop, where you update the agent itself and the parameters associated with the agent. And then in an outer loop, you update the meta parameters. So these parameters govern how the agent learns, and you update those on a lower frequency after you've done a sequence of updates for the agent. And an illustration of this can be seen here. So if we start up here, we can basically see our trajectory of improving thetas. So thetas are the parameters for the agent itself. So this is the inner loop that we're doing continuously in order to improve these parameters. And we start with some theta I, and then based on what our meta parameters eta are, we update our agent parameters to a new set of values. And we do this a number of times. So we go from theta I to theta I plus 1. And we do this a number of times till we get to, let's say, theta I plus m minus 1. So we do it m times. And what we do in each of these steps is we update the parameters according to their, we use gradient ascent basically to update the parameters. And the way we calculate this gradient is through an inner loss function. So we have some inner loss function that we use in order to gauge in what direction we want to update the parameters. And what you should note here is that the inner loss function here is parameterized by eta. So that's why we see eta in each of the steps here. So eta are the meta parameters, and they govern then basically what the loss function is. And depending on what the loss function is, the gradient that we update these parameters with is going to be different. So in conclusion, what we do in the inner loop is we update the agent parameters, and we do so based on the meta learning parameters. Now, once we've done this a number of times, we evaluate basically how good our procedure is for updating these parameters. And we do that through an outer loss function. So we follow gradient ascent on that outer loss function and then update our meta parameters, eta, according to that direction here. And then we do this a number of times. So each inner iteration improves the agent, and each outer iteration improves how the agent learns, or the scheme that is used to update the agent. So because of this, generally meta gradient RL algorithms are quite unstable or quite prone to instabilities, because you're using this twofold approach, specifically with the outer loop. And that's why they postulate then in the previous slide that using the target will be more stable. The next thing we're going to look at is how we can update or use this update target for prediction and value-based control. So what we can see here is basically that when we're in this setting, we would update our value function, which is parameterized by theta. So the value function is an attribute of the agent, and it is parameterized by the agent parameters theta. And we would update that toward our target, which we previously said would be parameterized by a deep neural network. And we do so with squared loss, or they do that in this paper. And that will give us the following update. So you follow the gradient of theta, and that is basically the difference here between your target and then your value. And well, this is the sort of size of how unexpected your value that you got is. And then you move in the direction of the gradient of the value function. So this is the meta network, and this is the agent parameterization. And you do this for M updates. So if we look back at the meta gradient algorithm here, we can see that we're updating in the inner loop now. So we're updating our theta parameters, and we do so with the inner loss function. And the inner loss function, which is the squared loss here, gives us that update. So we do that a number of times. And after we've done this for M updates, we use the outer loss function, and it's computed from the validation trajectory. So we denote that with tau prime as the square difference between predicted value and bootstrap return. So this is similar to the loss that you would use in a standard reinforcement learning application. So you have your bootstrap to return here, and then you have your predicted value function based on the validation trajectory here. And you, again, update this in the gradient direction. And we want to now plug this in to what we saw before for the meta learning, which is basically here. So we want to update our meta parameters in this step as part of the outer loop. What you can see here is that we have a gradient with respect to eta here. And in this equation, we have the gradient with respect to theta. But what we do in the setting is we consider theta as a function of eta. And that's been held fixed now. The eta has been held fixed for a number of updates to theta. And using the chain rule, we basically get this update. So we want to evaluate this property, but using the chain rule, we can make use of the expression we have here, and then also this term. So where we consider the, how theta will change as a function of changing the meta parameters. When we use this in an actor-critic setting, things become a little bit different. So we have an update target here that is used both to compute the policy gradient update, but also to update the critic. So if you haven't seen basically videos on actor-critic algorithms, we have multiple of those on this channel. So you can go back and watch one of those. There will be links in the description. But for now, we're just stating basically what the target would be. And so we have this target here where we have, similar to before, the difference between our target and then our value function. And then, taking that size of the difference according to, and multiplying that by the gradient direction in which we would update our agent. And then we also have regularization terms here. So we can see that C1 and C2 denote weightings of the critic's loss and entropy regularization terms. So here we have the entropy regularization term, and this is the critic loss regularization term. And the meta gradient then for this framework can be computed on the validation trajectory tau prime, just like before, using a classic actor-critic update. So once we take the gradient here, we get an expression that's quite similar to what we had in the last slide. And again, this expression is based on, is the outer loss function's differentiation with respect to the theta parameters, not the meta parameters. And what we would use then is the chain rule again to transfer this into something that we can actually update for the agent. So this is what they're making use of in the paper to derive the algorithm, and they call the algorithm Frodo. And that's what we're going to look at some results for right now. So the first thing we want to look at is a couple of toy environments just to test the functionality of this approach. Basically, the first of these tasks, which is called the catch task, is to catch objects that are falling. So you can see here that we have an agent, the orange one. It starts an episode in the middle of the screen here, and then you can move it left or right, one step per time step, basically. And then you have objects falling down here, and the object is for the agent to catch these objects. And basically to test the performance of this photo algorithm on, here, they use 10 independent runs with random seeds for each of them. So you get objects falling in different locations, and it's not predefined where they're going to come. And then you have basically your update targets. So the outer loss would be a full Monte Carlo return. So that is basically what we're using for, in order to compute the targets here for the outer loss. And for the inner loss, the agent only received 3 transition trajectories. And this is really important. So Frodo, like the algorithm, must discover TD prediction and bootstrapping since the game cannot be solved perfectly by looking ahead just 3 steps. So we get these, and you're not going to see how the game ends by just taking those into account. So you need to predict the future in some sense based on the information that you have, and then devise basically a learning strategy based on that. And to see basically how well this performs, they did a comparison to the best 3-step look ahead agent that they could construct So an agent that only looks ahead 3 steps and doesn't learn any of these TD predictions and bootstrappings. So any performance that is basically beyond this is an indication that the algorithm has actually learned how to bootstrap in some sense. And what we can see here is in the graph, we exceed, or they exceed, the best 3-step look ahead by quite a significant margin. And 1 here represents basically the best performance you can have. So if you catch this, you would get, an episode return of 1, which means that you performed as well as you can. So if we reach 1, that means we're basically performing optimally, and we can see that the algorithm reaches that point. So, this is indicating that it actually learns very effectively how to bootstrap. The second task that they tested this on is one where you have a non-stationary reward. So we can see the setting down here to the right. The agent basically starts in the middle at C, and then it moves according to a random walk in between here. It could end up in one of 2 terminal states, either the right one here or the left one. The right one is deterministic and has a reward of 1, and the left one is non-stationary and has a reward of either 0 or 1. And it switches these based on basically it switches them deterministically with a fixed number of iterations in between. And the idea was for Frodo to predict this value function using a TD1 update as the outer loss. And what you need to do is you must quickly then be able to adapt the prediction to whether left or whenever the leftmost reward switches. So either when it switches from 1 to 0 or 0 to 1. And Frodo learned an update capable of dealing with such non-stationary attributes effectively. And we can see that in the performance graph that we have here to the left. So we have a comparison here between TD1s with different lambdas here, and then we have a comparison to Frodo. And you can see that the mean squared error for this task is significantly better for Frodo than for the other ones. Even for the best one they were able to find, we're just using a simple TD1 update scheme. And we can also see here that this is basically the switching times for the agent. And you can see that the loss from Frodo is significantly less than for even the best performing TD algorithm. So, 0.4 is used in this graph as well, which is best performing here. And we can see a significant difference between them. And this basically tells us that Frodo learns about this non-stationary return. And that is one of the key benefits that we highlighted in the beginning. So if you remember, we said that we can update the objective as we go. And that is exactly what we're seeing an example of here. What they did next is they evaluated this on some more complex domains. So basically the Atari suite. This is a study based on the entire suite of Atari games, so all 57 of them. And what they're comparing this Frodo algorithm to is the Impala algorithm. So that is basically an actor-critic algorithm that's quite well-performing and commonly used. And what we can see is that the metagradient algorithm learned slowly in the beginning and then gradually discovered an effective objective. So we can see here that learning rate, is quite good at this range actually, where Impala tends to even out, and this has the effect of, in the long run, giving Frodo an edge basically over Impala. So it's a bit slower to take off in the beginning, but once it closes in on the proper learning scheme, it seems to actually do a better job in the long run. So those are very interesting results. And as we said, these are across all Atari games, so it basically outperforms Impala on that suite in general. The next thing they investigated was basically the performance of a subset of 8 Atari games. And what they did comparisons on here was basically whether or not the target or the loss function itself is preferred as a means of training the algorithm. So we discussed that in the beginning, that when you're considering reinforcement learning algorithms, you could either construct or basically parameterize the loss as a network, or you could parameterize the target as a network. They postulated that the target would be better, and we see an investigation of that here. So basically the 3 graphs that we can see here is the first one at the bottom is where they train or parameterize the loss function to actually be a network. The second one here, so the green one is, let's take the orange one first. That would be Frodo, so the standard algorithm. And this one is Frodo without consistency loss. And consistency loss is a regularization scheme that they apply on top of the Frodo algorithm, basically to make it a bit more robust. And what we can see here is that when you're learning the loss function, you tend to have significantly worse performance than what you basically have if you're using the Frodo algorithm. So as they postulated in the beginning, it seems to be much better to learn the target than to actually learn the loss function because of what we said in the beginning, or that's what they postulated anyway. So if you get a big loss, that could shake the algorithm such that it diverges very rapidly. The last thing we have here is basically an investigation of the discovered inner loss target and how that differs from the target used for the outer loss. So this is the same 8 Atari games that were used for the previous investigation, so in the previous slide. And we can see here that basically the difference between vtrace, which is used for the outer loss, and then the inner loss function here, g-eta. And we can see that in general, there's large variation both throughout training. So we can see that they vary a lot here depending on which sequence we're in, but then also across games. And it's only really in Pong where the target is close to vtrace. And what we see here is basically a log scale as well. So there's a significant difference between, let's say, Crazy Climber and Pong. And so in general, there is no strong correlation between these. As a conclusion then to this paper, they basically used the approach of taking a deep neural meta network and using that as the target used to update the policy and value functions in this reinforcement learning framework. And the objective then was discovered by metagradient descent over the update sequence based on this discovered target. And what they found in the paper was that there is potential to recover and discover. So both recover existing RL concepts, but also discover new ones based on what they saw in the results. From the toy domains, they were able to see that Frodo, which is the algorithm applied, learns to address key issues like bootstrapping and non-stationarity through online adaptation of its objective. So the bootstrapping, we were able to see that through the falling objects in the catch domain, and the non-stationarity was taken into account in the random walk sequence that we were able to see. Secondly, in the Atari domain, they showed that Frodo can discover and adapt off-policy learning objectives that are distinct from and perform better than strong benchmark RL algorithms. So we could see a comparison with Impala over the set of all 57 Atari games, and we had better performance with this new framework. So as a final remark, the online conclusion or the online setting that this was done in generally makes the results applicable to any RL application. So, what the findings are here are from a theoretical point of view, quite interesting in the fact that we can actually apply those to a number of different approaches, both on policy, but also off policy in the future. So that's it for what they had to present here. Thank you for watching and see you in the next video.